Oh, I can end it.
So we are live now.
Okay. Great. I wanted to say thank you everyone for joining, and thank you Ramses and Marcelo and everyone at SciNet for hosting this lecture. Today we're going to continue the Compute Ontario Summer School series and discuss neuroimaging analysis, so part of the original biomedical stream. We're going to talk about neuroimaging analysis at scale. And today I'm going to be starting off the lecture, and then it's going to be taken over by Michael Joseph, who is also on video. I don't know if you can see him. This material was put together especially by Michael and myself, as well as Jerry Chandra and Olivia Stanley and Jason Kai, through a process that we're now trying to make a part of data carpentry neuroimaging. We'll speak a little bit about that. You should be able to find, wait, I should stop. Exit slides. You should be able to find actually these slides, as well as all of the course code and information at our, the thing is talking, on the course website, which is the SciNet course website. And from this course website, you also should be able to find information for the course today, actually on this hack md.io page, where you should see links as well as additional links. And hopefully, I think we should have edit permissions so you can keep adding information here as well. Oh yeah, we have a Gather Town. I'm so excited. So Gather Town is a place might come back to it during the coffee breaks, and when the course ends, it's just a nice place to have smaller conversations afterwards. I'll come back to that. Okay, so back to today's information. So we're actually going to change up a little bit from this plan, and we're going to start by, for those of you who know neuroimaging, you're going to get reintroduced to neuroimaging a little bit. For those of you who are new to neuroimaging, I'm going to introduce you to this concept of neuroimaging, especially MR imaging. And then we're going to go from there because we're going to talk about something called BIDS format, the nomenclature of BIDS format. And then we're going to go in actually straight into some Python environments and start talking. Oh, there's Peter. Okay. We're going to start talking about how to actually start querying and working with neuroimaging data sets in Python to actually figure out some general information you're going to need from those neuroimaging data sets, like say how many subjects you have, or just to understand what is in the data set. And then we're going to actually talk about how to work with, a little bit about how to work with neuroimaging files. And that's all actually stuff we're going to demo today. Tomorrow, for the interactive component, we're going to be here to help you with potentially converting data to BIDS, but also with working with some of those Python packages as part of the assignment. And this next thing we're going to do, oh, cool. Finally, on Thursday, stay tuned because I think it's actually the most exciting part of this week. We're actually going to go full steam ahead and talk about neuroimaging preprocessing pipelines using containerized environments. So specifically, I mean using Docker and Singularity, and that information will be interesting for people interested in neuroimaging, but also just people trying to understand how to use Docker. Docker to build containers and Singularity to run containers on the SciNet cluster. Okay, so that's a lot of information. Before I start, wait, can I poll people? I don't know if I can poll people. Okay. Kind of show of, wait, can I do show of hands? I don't know if I can. So if we do a show of hands, oh, maybe in the chat. Can you tell me if you, yes or no, if you have any experience working with, oh, I can ask them to raise hands. Tell me if you have any experience working with neuroimaging data before, or MR data. We actually have have a pretty mixed bag of responses. That's exciting. Yeah, so we have complete newbies, which is exciting because then I get to teach you everything from the beginning. And for those who have worked with neuroimaging data, I'm going to reteach you some things because there might be some there's some shared nomenclature that I think will make this a lot easier for us to work with. Okay, so back over to my slides. Next slide. Okay. Okay, so to reintroduce you to neuroimaging data, actually what I'm going to do is take you to a website, which is quickly becoming every neuroimaging scientist's favorite website. It's called OpenNeuro. Actually, the link's right here. It's at openneuro.org. Everyone can go there right now. You can sign into the website with your ORCID or your Gmail ID. But I'm just going to take us to this public dashboard, which anyone should be able to see. And you can see there's actually a ridiculous number of neuroimaging data sets up here. All of these data sets are actually pretty much free to download right now. There's actually a button that you should not click because if you do, then you will start downloading gigs of neuroimaging data onto your local computer. I'm going to go to one particular data set, which is very popular. Actually, if I go to the public page, it's probably listed here as one of the most popular. Yes, it is actually the most popular. Okay, so the most active, it's been watched, oh my gosh, by almost 2 million people now, and downloaded a ton of times because it's a very interesting data set, is this UCLA Consortium for Neuropsychiatric Phenomics study. Which is a really nice study out of UCLA, which has done neuroimaging scans on multiple patient groups with a nice little battery, and is all publicly shared on the site. So, and see, there's a download button, and then you have the data. Yes, but this is a lot of data. You don't want to download it all at once. We'll talk about that. But I want to talk a little bit about the data that's in here. So we can see the file tree on the side. We'll go over these later. Okay. And actually, yeah, participants. So I should show you in this data set, we actually have, this is a TSV with information about all the participants. And you can see the most exciting thing, you have this diagnosis where we have control. Scroll down, there's about 100 controls. But we also have schizophrenia. We also have bipolar disorder. We also have people with bipolar disorder. And we also have people with ADHD. So it's quite an exciting data set to look at if you're interested in mental health, because you have quite a few groups represented. Wait, I'm going to take us back. And for all of these people, they did a decent neuroimaging assessment. The way we can tell this is that within, this is one subject, we have anatomical data, behavioral data, diffusion weighted data, and functional data. So we'll start with anatomical data. So this anatomical scan is something we could call a T1 weighted scan. It's the thing that we normally think of when we think of a neuroimaging scan. Should load. Yes. Although this person's moving a bit. But it's your classic, so T1 weighted stands, or T1W stands for T1 weighted. It's a type of physics that happens in the scanner. And it allows, it's the classic neuroimaging scan. We remember when we think that white matter, which is the stuff inside the brain, should show up white. Gray matter, which is where all the neuron cell bodies are, shows up gray. And you can see things like the skull and fatty tissue. And also, you'll notice the face is missing from these scans. That's on purpose. That's essentially the only ethical barrier. That's in order to hide the identity of the people who've been scanned for ethical reasons. And it's essentially one of the only things, the only data use things you need to think when you're using OpenNeuro is that you should not try to identify these people. That's literally pretty much the only line in the data use agreement. Okay, so that was anatomical data, but within this subject, we also see something called functional data. Functional data is something called fMRI. And in fMRI, we have a different story where instead of trying to look at the brain as one box, we're actually instead of trying to take a nice high resolution picture of the brain, we're trying to take a low resolution movie. Specifically, our movie, or what our movie's capturing, are blood flow patterns in the brain. That's why we call it BOLD, or blood oxygen level dependent. And actually, we can play this movie in this viewer, which I think is here. You can see the frames don't change that much. They're very subtle changes in blood flow from time to time, but you can see that it's changing a little bit. Okay. And the third major type of neuroimaging data that we can work with, or that exists in this data set, is something called diffusion weighted data. In diffusion weighted data, what gets captured, and maybe I need to describe this, maybe I should describe the data and come back to it a little bit more. Okay, yes. So what happens in diffusion data, I'll come back to it because it'll make sense when you see the scan if you actually know what it is. Let's go back to anatomical data. So in anatomical data, we know we have a three-dimensional image. In each three-dimensional image, there's little cubes or pixels. So when a pixel is three-dimensional, we call it a voxel. So there's voxels. And the T1 weighted is most common. The T1 weighted is the one on the left here, where white matter is white and gray matter is gray. But there's also other types of anatomical data, like say this is called a T2 weighted image. Okay, I told you about functional data, and that's where we're looking at blood flow. I'll come back to this. And then in diffusion data, this is where we get the really pretty pictures of the brain. And we do this actually by tracking water diffusion through the brain. So if we go back to the OpenNeuro image, so what we do is actually, we take a four-dimensional image where every dimension is a measure of how much water is able to diffuse in every direction. So if we move through, so this is an image where everything's able to freely diffuse, or free diffusion a bit higher. So you see that in the parts of the brain that are water, you see them show up darker. And then as we keep going through, actually I'm gonna have to change the contrast here. Make it show up. Nope, other way. Yeah. And then as we move through these volumes, all of these volumes represent, for every point, how much water is able to diffuse in a certain direction. So by putting all of these things together, if we know what direction water was allowed to diffuse in, and we put together these three-dimensional images, what we can actually track is for every point in the brain. We can try to model how much water is diffusing. Okay, we can try to track how much water is diffusing, and if we know how much water is diffusing, then we can use that to try to understand what are the white matter pathways in the brain. And we can make these pretty images like this one on the right, and like one I can put in behind me. I'm going to change. We can track these directions where water can diffuse to try to figure out where tubes exist and where water is diffusing in the brain. Okay. Let's see. So actually, is darker greater diffusion or white greater diffusion? That's a good question. So diffusion is measured, the amount of diffusion is measured as Yeah, so sorry, white would be more diffusion, because we see more diffusion in we see the most diffusion actually in the cerebral spinal fluid, where diffusion is the most free, where the most diffusion is happening. Okay. I'm trying to think how this works. Okay, we'll have to put together. Actually, diffusion is something that we can come back to in some other notebooks later, and Michael will remember, because he does more diffusion work than me, exactly how diffusion works. Oh, but the classic thing that we need to remember is that in order to actually work with diffusion data, we need our four-dimensional images, where we have our reference image, and then we have all of the directions of diffusion. But yeah. And then what we also need is what we call something that we now store in FSL. We call them bval and bvec files, where bval is how strong the magnetic gradient was, which is trying to force this diffusion, and a bvec file stands for vectors, which is actually the direction that the diffusion is happening. And we need that information in order to actually work with the data. Coming back to the functional data, one thing that I forgot to say is that when we're looking at this movie, we usually care about it in relation to other things that are happening, what's happening in the scanner at the time. Sorry, I'm going a bit all over the place, but when we look at Bold or these movies, what we really care is what's happening during that movie, and we usually can't actually do an analysis of that data unless we understand what's happening with that data. Okay. Yeah, and we usually can't analyze functional data or fMRI data unless we know what's happening at the time. Sometimes we just care about whether or not things are correlated with each other, whether or not one part of the brain is correlated with the other part of the brain, and people could be doing anything there. So sometimes we give them nothing to do, and we call that task rest or resting state. But most of the time, but a lot of the time in functional data, we actually are giving them a task to do, and that task is very important for the analysis. So it's really important that we actually have corresponding information about what is happening outside the brain, what the brain is looking at, what the brain is trying to do while this movie is playing. So with those things to keep in mind, I want to introduce you to something called the brain imaging data structure. So brain imaging data structure, or BIDS, is a way to organize and understand neuroimaging data. Okay. Okay. So from those, so the brain imaging data structure came into play actually mostly because of that OpenNeuro website. Because when they started posting data, they realized that they needed to create a way for someone to be able to download the data and work with it without having to email and have a long conversation with the original authors. So they started thinking about what are all the things you need to describe about a neuroimaging data set, and they started thinking about what would be the easiest way to make that data describable. And they came up with a way that you should name your files and a way that you should organize your files that would be a standard, that would be a structure that hopefully other people would understand. So if we look at the brain imaging data structure, there's a couple of reasons why we should use it. One is so that we can share data, not just with other people, potentially our collaborators, but also potentially with ourselves in 6 months. There's a great quote, which I forget to put here, which is your number one collaborator is yourself 6 months from now, and that person does not answer emails. So the most consistent you can be with the way that you name your files, the more likely you are to understand what you did later down the road. The other thing that happens, which is nice, is that the BID structure tried very hard to not reinvent the wheel and to not change things that were becoming common. So they use file formats and conventions that were already becoming common in the neuroimaging community, such as using the NIfTI or the Neuroimaging Informatics file, the NIfTI file format. Okay, and another thing, which is something that we're going to talk about later when we get into Python, is because we can do things very quickly that we couldn't do before we had our data bits converted, to use tools to actually query what's going on in the data. So to figure out how many subjects we have, how many tasks we have, and if any of our data is incomplete, if anybody's missing something. Okay, and the other reason, and this will become much more obvious on Thursday, that we use BIDs is because now we've started building our pipelines. A lot of open neuroimaging pipelines, some of the best pipelines that exist, actually work specifically with the BIDs format, and will not work if you don't have your data in BIDs format. So a lot of people end up converting their data to BIDs just so that they can run pipelines. And I'm excited about this because it actually meant that I feel that pipelines got more complex under the hood. So they were able to do much more exciting things, with fewer command line arguments. And the reason they could do that is because under the BIDs framework, the pipeline will actually read your directory structure, and from your directory structure, it'll see if certain files that it wants are available and decide whether or not certain flags are more appropriate, certain flags or certain arguments to the pipeline are appropriate for your data set or not, instead of putting that onus on the user to figure out for themselves. Okay, so this is a description of what the BIDs data structure looks like. And we're actually going to go through this a lot more tomorrow with some tutorials to talk about how to do this. But if we think about this as usually the kind of data that we actually take off the scanner, usually in a DICOM format, this is what the data tends to look like in BIDs format. So there's a specific folder structure after we convert the files, and there's a naming principle. So here's the folder structure. We'll see this when we go through OpenNeuro as well. The data set name always goes at the top. And then underneath data set, the next level is always subject, and subject is always preceded by sub. And sorry, through the folder structure, there's a naming convention, and there's these key value pairs. So sorry, with the naming convention, under the folder structure, underneath subject, at this point, actually, we don't see it here, but underneath subject, you can have session for longitudinal decides. And underneath session or subject, you have your neuroimaging file format types, major types. So we split anatomical, functional, and diffusion data. And we also have specific key value pairs for a lot of things that are common nomenclature in neuroimaging. So sub stands for subject, and anat stands for anatomical, func stands for functional, DWI stands for diffusion. Task is a very important key value pair that needs to exist in functional scans to tell people what's happening. There's set suffixes within BIDs, and there's this idea of additional data on top of the actual neuroimaging data, which is really important to understand. So for tabular data that we need to use to describe our data set, there's TSV or tab separated files. And for additional data about each image, which we can't understand as well as a table, we use these JSON file formats, which lets us hold dictionaries or unstructured data about those scans. And if we go back to OpenNeuro, we can see examples of these from our data set. So going back. We can actually view them and query them pretty fast. So for this anatomical scan, we could see the scan, but we can also view the sidecar JSON. If we view up, it has all of this information about the scan itself. Some of this is required, some of it is optional and just automatically gets put there by file converters. And another thing to understand, so for our functional data, we have, yes, for something like an event, for something like a task, SCAP, we have a table which tells us the onset, the duration, and trial, so things that were happening during the event. And this is in a tab separated area. Okay. So I said this is important. You can go to bids.neuroimaging.io for instructions, but the best place to actually get wait, does bids.neuroimaging.io still work? The bid standard actually is now, it should be the first thing that comes up. Yeah, so it's now actually bids.neuroimaging.io has entirely moved to this website. It used to be this huge PDF, but now actually the specific and all of the information about how to do it more specifically is in this huge PDF, or this huge specification here. And so this describes in a lot of detail all of the rules that go into bids, or all the rules that people have discussed in bids. And the other thing that comes out back, which is interesting to go to, is something called the bids starter kit repository, which is something we're going to go to soon, which contains really, really excellent tutorials to get everyone started with this file format. So actually, one of the things we're going to do tomorrow is, as part of the assignment, is to actually go through and try to understand and try to actually bids convert something. Because when you actually do try to convert an example data set to bids, you see how simple the conversion is, and you start to understand all of the underlying principles. Cool. So just to discuss a couple things about bids conversion ahead of all the excitement of trying it for ourselves tomorrow, is that the nice thing about bids converting a data set is actually that they built it in a way that that is very straightforward. You should just be able to convert from DICOM and rename the files if you want to. So there's actually no programming needed. So with no programming, there's no excuses not to do it. And there's an example how to do it completely with point and click in the first tutorial of the bid starter kit. So if you don't want to do the programming example, you can go straight to tutorial 1. After you do tutorial 1, and this is very nice in general, is that there's something called a bids validator. Oh, that works. Okay. So so a bids validator, this is actually something that this is a web app that entirely works client side. So you're not actually uploading your data to a data set when you run this, but you can choose a file on your file system. Actually, I don't have some downloaded bids data that I usually use to demo. But you can bids convert your data, and in the tutorials you do this, and then you can point this validator to the folder, and the validator will tell you whether or not your data actually is bids valid. Another thing, so it's very, they made the whole process very straightforward. And when it tells you it's bids valid, it also tells you some really interesting other things about your data, like whether or not you have missing subjects. And the bids validator is something that not only can run on the internet, but it's also integrated into a lot of pipelines. Okay, the second method, and this is kind of an ad hoc programming method, is that you can, the ad hoc programming method, and this is one that we end up using a lot. If you have a data set that you already have in NIfTI format, and you don't have the original DICOMs, you can still bids convert the data set by doing a couple things by just renaming all the files, so putting them in the file format convention, and essentially baking it till you make it with this sidecar information. So going through the PDFs, figuring out what is the sidecar information that you need, so to hand write the JSON files with just the fields that it needs in order to pass the validator until the validator passes. And BIDS has something useful called an inheritance principle, which is very useful this way. I'll demonstrate this a little bit. So if this is a way that you want to work, this is another tutorial that you can work through tomorrow. And this is actually available in a markdown file. So this process of just renaming the files and adding a couple extra metadata files should allow you to do the bits conversion. And what was I going to say? Oh yeah, and you can see examples of the inheritance principle actually also in this DS data set. So if we go back. So inheritance principle means that if you put a JSON at the top level of a directory, so in this case, this task BART JSON. So for the BART task of this fMRI, so for this BART task, everybody did the exact same thing in the fMRI. So instead of putting a BART JSON beside every single fMRI file that used this BART task, you can put this JSON at the very, very top of your folder structure to describe the task, and then that information is actually inherited or understood by all of the files that have task BART in the name. And we'll actually see examples of how the inheritance principle works a little bit better when we start actually querying datasets with the Python package PyBits. Okay. And the last one, so this is an example. And the last way is that there's, because this has been happening for a while, there's even fancier ways to BIDS convert your data set. So there's Python packages like qtconf to actually create templates to make scripting the BIDS conversion process, so scripting the renaming of files, happen a lot easier. There's something called xnat to BIDS, which tries to BIDS convert as things get pulled down from xnat. And as you're going, the last thing I wanted to say is point you to something called neurostars.org. Neurostars, best thing out there. So Neurostars is a discussion board. It's the nicest discussion board support forum out there. It's run by INCF. It's supporting a lot of educational things, and I just feel like everyone who goes on Neurostars is there because they're bored and happy and excited to answer other people's questions. Whereas if you try to email the developers directly, they might be busy or grumpy that day. Everyone on Neurostars is super friendly. And it's a great place to get kind of crowdsourced advice on everything to do with neuroimaging analysis. Okay, and then I'll just set us up for the main reason why we're using BIDS is because on Thursday we're going to start discussing other ways that we can work from BIDS, including using BIDS apps, which are containerized pipelines in the way that we preprocess our data. Okay. So with that said, actually, I think I'm going to stop sharing my screen and turn the mic over to Michael, who's going to start telling us about Python packages to work with these data sets.
Hi, everyone.
Okay. Yay. On brand. Okay. Okay.
Okay, I'll share a link to the workshop materials in the chat.
Yay.
And so today we're going to use Binder. We've created an environment with all the software dependencies and Python packages already installed. So this will help with setup time. But if you decide down the road that you want to use some of these packages in your own analysis, we'd be happy to help you set up either after the workshop today or tomorrow during the interactive component.
Yeah. And we should
So,
mention that there's a link in our notes to a document about setting up those environments too.
yeah. So if you guys open the hackmd file, the very first link also shows you the set of instructions. But I can walk everyone through it as well. So here's the link to the workshop materials. It's at github.com/carpentries-incubator/sdc-bids-intra-MRI. And we're just going to click this link, the launch binder icon. And this might take a bit of time, depending on your internet connection. But the benefit of this is that it'll give us a space to work with Python code, text files, and the terminal all in one. So I can't see the chat, but if you can post in the chat whether you've got this screen going. Cool, looks like it's loading for most people. So now we're gonna go into the code folder. And then we're gonna click on the second folder, Anatomy of NIfTI. And we're gonna click on this IPython notebook, Anatomy of a NIfTI. Everyone good so far? So yeah, as Aaron was saying, the hope of these 3 workshops is to start introducing you to some tools that have already been created and are starting to be used widely, so you can get started really quickly with your own imaging analysis. I'll give it a couple minutes for everybody else's environment to load. But yeah, for some of you who are familiar with working with neuroimaging data, you'll know that when the data comes off the scanner, it comes in the DICOM file format. And somebody posted in the chat, we'd use DCM to NICs to convert the DICOMs to NIfTIs. And from there, the NIfTI is a much easier file format to work with. It's just one single file with all of your data captured in it. And it can hold 3D or 4D data in a single file. And with this notebook, we'll talk about some of the different components of a NIfTI. So the package that we're going to use is NIBabel. And this is a package that was created to read NIfTI images and manipulate them in different ways. So I'm going to import my Python package in this line here by typing import NIBabel as nib. Oh yeah, and somebody posted in the chat, is there a difference between DCM to NI and DCM to NICs? So the DCM to NI is kind of like the original DICOM to NIfTI converter. DCM to NICs is the one that has kind of replaced it and is being updated more frequently. So that's the one that we tend to use. I think there are some cases that we might fall back on DCM to NI for some kind of problematic scans, but for the most part, we tend to use DCM to NICs. Oh, and also I should mention what we're viewing now is a IPython notebook, and there are a couple things to know to get oriented. So you can have 2 different types of cells, code cells and markdown cells. So in the top here, I have what's called a markdown cell, and you can see that right there. And this is just cell that's rendering text. Over here, I have a code cell, and this is code that's a cell that's rendering code. If I want to run any commands, I can click on the cell that I'm interested in and click on the run command. Or if you wanted to do it using your keyboard, you can type in Shift plus Enter. All right, so the first thing that we did is imported the NIBabel package, and we gave it an alias called nib, just so that we don't have to type it out all the time, every time we want to use some of the functions in it. The next thing that we're going to do is we're going to load a NIfTI file. So I'm just going to go back in to the repository, and in the data folder, we've saved a random T1 weighted image, and that's the file that we're going to load in. So in order to access the load command, I'm going to type in nib.load, and then I'm going to give it the path to that NIfTI file. And if you want, while you're typing, if you press tab, it'll automatically complete the rest of the path. It's pretty handy for if you don't exactly know where things are and how things are spelled. And to run it, I'm just going to press Shift Enter. And you'll see that it gives us a special NIBabel NIfTI object. And we can access different bits of the object in different ways. So one other thing is I'm just going to save this object under a variable called T1_image, just so that we can access it later. And I can show you the different attributes of the T1 by typing in T1_img and clicking tab. So there's a whole bunch of things that we can access. The first thing that we'll start with is the header. So I'm going to call it our variable header. And I'm going to print it out to the code. Oops. So this is the header. It tells us some basic information about the NIfTI, such as the dimensions. So we know that it's 57 by 67 by 56. For its pixels, it's a 2.75 by 2.75 by 2.75 millimeters. And you'll see that, so the way this is written out, the T1 header is a Python dictionary. So dictionaries are kind of similar to the JSON files that Aaron mentioned earlier. They contain key value pairs. Oh, Ramsey says that he's not getting the binder environment. Is anybody else not getting the environment? Can't type in the code blocks. You might have to refresh the page, Ben. Oh, okay. I'll keep going with an explanation. So as I was saying, T1 header is a Python dictionary that contains key value pairs. So similar to how we access the attributes of the T1 image, we can do the same thing with the header by typing T1 header dot and then the tab. So the first thing that we're going to do is see all of the keys in our header by using the keys method. So we can see that we have all of these different keys that we can access. And now say we want to get the pixel dimensions for the T1 header. We can type, we can do this in two ways. One is T1 header and then the pixdim field. I think we can also do T1 header dot get. Yeah. So now that we've seen the header, the second major component of the NIfTI is the data itself. So to view the data, we're going to use another method, T1 image underscore get f data. And if I print it out, it's going to show us the value of each, I guess, individual voxel in the data. If we want to do, if you want to know more about the different methods, what we can do is put a question mark in front of our command and type in the function name. Oops. So this will show us all of the different, sorry, it's meant to be typed in without the brackets, but this will show us all of the different arguments that we can do. So by default, our data is returned in the float format. But if we wanted to, we can also change the data type. I'm just going to import NumPy. Okay, there is a way to do this. It's not working at the moment, but yeah, you can even change the data type as you're importing the data. So we can also look into what type of data this is by calling the type command on T1 data. And we'll see that it's a NumPy array. So NumPy is, an array is used to sort lists of numerical data into something like a table. And next we can check out some of the attributes of the data array. So if we type in T1 underscore data and then click on tab, we can see all of these different methods that we can access. So the first thing that we can check is how many dimensions are in our T1 by using ndim. This tells us that our data is 3D. Okay, so one other thing for the people who are kind of falling behind, one other thing that I want to point out is for this notebook, we have a solutions folder. And this should have updated instructions with all of the commands pre-filled. So you can catch up that way. Also, how's the text for everybody? Is it too small? Try making it a little bit bigger. Yeah, sorry about that. I didn't think to enlarge it earlier on. Okay, the next thing that we can do is look at the shape of the data. So we know it's 3 dimensions, and each dimension is 57 by 67 by 56. So these numbers represent the values along the X, Y, and Z axis. So what this tells us is the brain was scanned in like 56 different slices. So if you were converting from DICOM to NIfTI, you'd have 56 images. Each image would have a dimension of 67 by 56. And it looks like it would have a total of 213,864 voxels in total. And this isn't even really high resolution data, but that's a lot of voxels. So next we can see the data type by typing t1_data.dtype, and we'll see that it's float64. So that refers to how many decimal places can be stored and how precise that data is. So Marie's asking, is the height 57 or 67? I'm not really sure at the moment, but when we plot it out, we can figure that out. So the next thing that we can do is find out what the min and max values are of the data are. We'll import NumPy to do this. And to get the min value, we'll use the np_min function. And then to get the max, we'll use the np.max function. So for our data, the range in densities goes from 6 to 96. So the next is, how do we examine a particular voxel? So we saw that the data itself looks like this. And the way you can think about accessing individual values is, say you were looking at an atlas or like any map, and maps have different coordinate systems. So say you're looking at like box 2, 3 to find a particular region. That's how we can also investigate our data. So if we're interested in a specific coordinate, say 10 by 20 by 3, we would type in t1_data 9, 19, and 2. And the reason I'm not typing in 10, 23 exactly is because in Python and maybe in some other languages as well, values start from 0. So your first value would actually be 0. The second item is 1, and the third item is 2. So it looks like the intensity of our voxel at this particular coordinate is 32. So the next really important thing is what we're going to do is called slicing. So what slicing does is, given our 3D volume, we want to pull out 2D slices of data. So in this figure, you'll see the data being sliced from right to left. And so for our sake, what we're going to do first is try and pull out the 10th slice in the x-axis. So I'm going to call this x underscore slice is equal to t1 data 9 for our 10th slice. And then because we want everything in the y and z axes, we're going to use this colon, which means everything. The next thing that we're going to try doing is do the 20th slice. So if anybody wants to post in the chat, how would they do that? Oh, I think the one thing that you're missing, James, is the brackets after T1 header. Yeah, Katie, that looks great. So our x slice is going to be semicolon or colon. Y slice is going to be 19, and our z slice is going to be colon. And finally, the z slice is T1 data colon and 2. So now that we've picked out 3 slices, what we're going to try to do next is to plot them. And to do that, we're going to use matplotlib. It's a really popular plotting library in Python. So the first thing that we're doing here is importing matplotlib, the pyplot function from matplotlib. And we're using this %sign matplotlib inline. This is a kind of what's called a magic in Jupyter. And this is going to actually show our plots in line with the text. The next thing that we're doing is grouping all of these slices that we created, the x slice, y slice, and z slice, into a list using these square brackets here. And for each item on the list, we're using matplotlib to plot them. And this is what we see. So our x slice is a sagittal section, our y slice is coronal, and our z slice is axial. So yeah, somebody was asking earlier whether the height of the image was 57 or 67. And it looks like the height is 57 in this case, and the depth is 67. So yeah, all of this kind of will depend on your affine matrix, which is what we're going to come to next. This is kind of, apart from the data, this is also one of the most important pieces of the NIfTI image. So we'll use the affine method to grab it. Oops. This would be T1 image. And it looks like our affine matrix looks like this. So one thing that what the affine matrix does is, if you recall, our x is the first dimension, our y-axis is the second dimension, and our z-axis is the third dimension. But when looking at this image, we had no real idea of, whether something is on the left side or the right side, whether something is going to be, whether the height of the image was 57 or whether that was 67. And the affine matrix is the one that really helps us understand this. I guess in major cases, say you'd had a lesion in the brain and you want to know which side was the left and the right, this is where the affine matrix would really come in handy. And so it allows us to translate between voxel coordinates. So say we had an image that had coordinates 0, 0, 0. That would be if you had your image here, 0, 0, 0 would be the very center of our image. And if you want to translate that from voxel coordinates to actual world space coordinates, so finding out which is left, right, which is top, bottom, or which is front, back, this is when you'd apply the affine matrix. And so this guide explains it in more detail, but one of the common coordinate spaces is called RAS. And in that coordinate space, your values move from left, your coordinates go from left to right. So more positive values would be on the right side in the x-axis, on the anterior side in the y-axis, and on the superior side in the z-axis. So in this example, say you had two coordinates, 90.23, 0.2, and 2.15. Your second coordinate was 10.25, 30.5, and 9.2. And you wanted to try to move from one coordinate to the next. You'd have to move 70.79 voxels to the right, 30 voxels posterior, and 7 voxels inferior. So that covers the anatomy of NIfTI. Did anybody have any questions or while they were trying to catch up? The next thing that we can try. Yeah, so Ben asked, will this notebook be accessible to us over the next few days? And yeah, we're planning on keeping it open on that GitHub repository. So it'll stay there forever. And yeah, we're continuing to update it over time as we find what things work and what doesn't work. And Maurice asks, in the affine matrix, are there 2.75 along the diagonals just stretch it? Yeah. The next thing that we're gonna talk about is OpenMRI datasets. So we'll kind of get into this briefly, but we'll give like a brief guide on it. But tomorrow you'll be using this code yourself for your own bits converted datasets. So while Jerry's explaining that, I went back to code. I clicked on number 4, Open MRI Datasets. And I clicked on the O4 Open MRI Datasets notebook. If everybody can post in the chat whether they've managed to find this notebook. Cool. So we're gonna go through bits and pieces of this just for whatever is relevant. But the first thing that we're going to do is use DataLad to download a dataset from OpenNeuro. This is the same dataset that Aaron mentioned in her slides earlier, DS00030, like one of the most popular datasets on OpenNeuro. And DataLad can do way more than just downloading datasets, but we'll kind of touch on that later. So the first thing I'm going to do is run this command. It's going to cd into our data folder and then download this dataset into the DS00030 folder. So now if I ls, and the reason you see these exclamation mark commands is these are actually not Python commands, they're bash commands. And this exclamation mark allows us to run bash commands in our Jupyter notebook. So I'm just lsing to see what files are available in our dataset. And it looks like we have all of these subjects. We have a description of the dataset, a list of participants, README, changelog. And I'm just going to skip down to this part. So querying a BIDS dataset. And so PyBids is another package in Python that's used to query BIDS datasets. So we can use it to grab any specific subjects, tasks that we're interested in, T1 or T2 file for T1 or T2 files. And a lot of the BIDS apps that Aaron mentioned actually use PyBids under the hood. And that's how they kind of grab the data that they want to preprocess and figure out which workflow needs to apply to it. And yeah, and Ben asks, when you download the data with this notebook, is it being installed on my actual computer or on the cloud? And in this case, because we're in Binder, it's being installed in the cloud. But if you ran that command in your own terminal, it would install it on your own local computer. I forgot to mention, one of the real benefits of using DataLad is that it doesn't download, it downloads the files, but actually, if I were to open a new terminal, oops, and I'm just going to navigate to the data folder, the DS0030, and you'll see that all of these small text files have been downloaded. But let's say I go into a particular subject folder. I'm going to go into the inat folder. You'll see that we don't actually have this NIfTI file. The instructions for putting it into our file system are there, but we haven't actually downloaded it yet. So what DataLad install does is it'll download the entire dataset, but only these small text files. And then from there, you can decide which subjects you want to download in particular. So that way you can see the entire dataset without kind of committing to all of that storage space on your hard drive. So I'm going to load in PyBids. I'm going to import that. And I'm going to query our BIDS dataset using the BIDS layout function. And I'm going to save the results of the query to the layout variable. So this query can take a while depending on the size of your dataset, or how many modalities you have, or how many acquisitions. So for really large data sets, it's a little bit suboptimal, but it can take maybe an hour to query. I think this one will be a lot quicker. We wouldn't want to wait around for an hour. But if you are reusing the same data set and you're not adding any new subjects to it, what you can actually do is after you've run this query the first time, you can save the results of the query to a SQLite database. That's what I'm doing in this command. And from there, the next time that you want to load in the database or the data set, instead of just feeding it the bids path, you can also feed it the path to your SQLite database. And that way, the query will run instantly because it's already been saved on your folder. So while this is running, I'll kind of just run the next few commands and walk through what the results are. So this next function is querying. So she asks, can we do modulo datalad on the cluster? That's something we're kind of getting in the works. So datalad is installed in your Python environment, but what it needs under the hood is git annex. So there is a version of git annex installed on the cluster, and you can modulo that, but it seems to be too old to work with datalad. So what we're trying to do is update the version of git annex, so that way you can use datalad on the cluster. If you were running this on your own local computer, what you do is first install git annex and then install datalad in your Python environment. So the first thing that we're doing here is getting a list of subjects. So I'm going to do layout.get to get all the subjects. And the next thing that I'm doing here is instead of getting all the subjects, I'm just typing in get, and this will give us all of the files within the data set. So this command isn't too useful. What you might want to do is filter those results. So layout.entities allows us to see what kind of key value pairs we can use in order to filter out from this huge list of files. So we can query for specific subjects, sessions, tasks, acquisitions. If we have multiple T1s, we can query for run 1 or run 2. Different modalities, so your NAT files, your diffusion, func, or bold. Different extensions, so you can query all of your JSON files or your NIfTI files. So now from this example here, I'm really paring down what happens, what we get back from the get function. So for our data type, I'm only querying the func folders. Our suffix is bold. So within the func folders, I'm getting all the bold files. I only want the resting state task. I'm only asking for the NIfTI files. So the file format extension is the ni.gz. So in this case, no JSONs will be returned. And I want the file itself instead of this kind of weird bids object that it's giving me here. So that's what this is giving. So the next example, what I'm doing here is querying a specific subject. You'll notice in the query, you wouldn't put in the sub dash, just the kind of value that's associated with the subject. Here, I'm also querying for specific things in the JSON file. So things like the repetition time of 2 seconds and all the files associated with that. So yeah, if I keep on scrolling down in the list of possible entities, there's a lot here, but I think you can even query, you can even use the JSON key value pairs to query specific keys. So Katie asked, what other files are within the func folder other than bold? And so in the func folder, we just have bold files. I think you could also have SBRef files as well. And that's like a different type of scan. But the majority would be bold folders. And if you wanted to know more about like what specific suffixes can fall in to each modality, you can go in the BIDS file format, go to MRI, and I think if you, each of the different kind of modalities, so a NAT lists the suffixes that are available to it. So now in bold, oh, sorry, I was wrong. So in the bold, or in the func folder, you would either have the bold suffix, CBV, cerebral blood volume, or any phase information. So in this case here, what I'm doing is I'm taking the first result, so indexing 0 of this query. So I'm just getting this file, the BART task, and we can get all the JSON metadata from it by typing out layout.get_metadata and then the name of the NIfTI file that we want to get the metadata from. So here we can see that the JSON file has all of these values in it. Some of it gets created by default by dsync to NIX, but you'll see that there's some kind of custom information that the uploads of the data have added, such as the instructions of the task and the task description. So this is kind of really important information when you want to share your data with other people, getting them to understand, getting them to understand what exactly is inside your data. So in the JSON file, you can have all of your standard MR scanning parameters, but you can also have custom fields that better explain your data. And the next thing that I'm doing here is putting all the metadata for all the fMRI scans into a data frame. And for this, I'm using the pandas function, which allows you to create data frames in Python, create and read data frames. So I'm creating a list of all of the metadata. I'm grabbing all of the fMRI files. And then here for each fMRI file, I'm reading the JSON file and appending the results to this list. And then from there, I'm creating a data frame from this list of lists. And that's what this looks like. So I think a lot of times when it comes to your papers, you might want to know what scan parameters were used for different modalities when you're writing the method section. So this is some handy code in order to do that for you. And you can filter for unique values to see whether things were consistent across your study or not. And I think that's all I want to get into for today. So for tomorrow, we'll be guiding you through converting a BIDS dataset. And we already have a BIDS dataset loaded onto, some DICOM files loaded onto Sinet. But I think if you also had some of your own data that you'd be interested in BIDS converting, feel free to bring that as well, and we can help you convert it. Oh, and Aaron asked, does bids layout to DF not work anymore? I'm not sure. I didn't know about that function, but that's something we can try out tomorrow as well. Does anybody else have any other questions?
Cool. Oh, so thanks, Michael, for all of this amazing. You got through everything like right on time too. So this is pretty cool. Oh, we wanted to say, so we have a link. We have a link to a GatherTown. GatherTown's like, it's like a coffee. It's like an online coffee break. You get to move your little like Zelda character around and talk to people, where we can have kind of a conversation. We can kind of have a conversation at the front of the room or outside in the hallway that we usually have. Password is brains. And the video chat won't work until you close Zoom, but it's pretty cool. So if you want to come ask us questions in person that you're shy to type into the chat, come join us there. And we really look forward to seeing you tomorrow when we go through these exercises, and on Thursday when we actually talk about preprocessing and working with Singularity containers for that. And I guess that's the whole thing. Do the sign-up guys have anything to add? Oh, and the attendance test number is 7. Cool. I think that's everything we wanted to say. So thank you a lot for joining us, and thanks for the great questions to keep things going. And we'll see you in GatherTown. Okay. Cool.